Good morning, everyone. Welcome to the AGL All-Member Meeting, Day 2. My name is Moeller, and this talk will be about reproducible builds and SBOM, and why you should care about both of them. Quick introduction. I'm Moeller. I'm the release manager for AGL, and I also represent AGL on the Yocto project advisory board. If you want to reach me, there's my email. The slides are on SCAD, so you can download the slides from the event schedule. So I want to talk about reproducible builds, about software bill of materials. What is that? Yeah. How we can do software bill of materials with BitBake and Yocto, and why do those two topics actually go so well together? So, reproducible builds. Well, it means that from the same source, with the same configuration, we get exactly the same binary output. Essentially, our whole build process system, however you name it, is then deterministic. Which means I do a build today, and I do a build tomorrow, and the outcome is the same. Or I do a build in X years, and it's the same. Or I do a build on my laptop versus I do a build on your laptop or on my home machine or on server X. Outcome is the same. Well, that's what we want, right? Now, wait. Why is that then not always the case? Now, the answer is, it's not that easy, right? I'm using SUSE, right? You're on a Mac. You're using Ubuntu. Your server is using insert whatever you like. So the host is not the same. Well, as a developer, I want to know from what I built this from, because I have like 20 versions of this binary or this source tree lying on my machine while I develop, and I forgot the folder from where I built. And you know, during development, you have like 20 different versions lying around, and you want to know where this is, when you built it, on what machine, and so on, and so on, and so on. As a developer, yes, I want to exactly know that, because tomorrow when I look at this again, I forgot where I were yesterday. Yeah. So, as a developer, I would add all of this information. Is that reproducible? No. If once you rebuild this on your other machine, the host name is different, the user is different, it's a different date, it's a different commit, it's a different folder. So at that point, it's a different binary, because we embedded, non-reproducible information, right? In principle, the less, the better. So this is just one aspect. That's more or less an aspect that I, as developer, can influence, right? There are more. So this is just the tip of the iceberg. For example, the compiler might insert a build ID, and so on. I just mentioned the build ID. There are also path-specific information, the so-called debug symbol prefix path. So there are way more pieces to the story of having reproducible builds. And this is just GCC, or well, C compiler, C++ compiler. If you have kind of a more recent language compilation system, they are on their path to being fully reproducible. Yeah? So newer languages like Go or Rust, their compilers are not even reproducible. They might do the same thing. They have some path that they embed. Yeah? Or they embed the compiler version or a compiler hash or whatever. So we have similar problems here everywhere, in the compilers, in the languages, in the tooling. So there's a project called Reproducible Builds. You find more information on the site reproduciblebuilds.org. And that's a project that bundles all of these efforts across various distributions, Debian, Red Hat, SUSE, Ubuntu, you name it, and various projects, because it's not a distribution problem, it's actually a problem across a lot of different a lot of different levels. Now, AGL is building using the Yocto project underneath. So the Yocto project has strong support for reproducible builds. Open Embedded Core, the essential set of tools, libraries, is fully reproducible. Like 99.9% of it is now fully reproducible, and it's being tested for that every single day. If you go to reproduciblebuilds.org, find the subpage with the distributions and then the Yocto project. It links to a page where you can see the statistics for the Yocto project. And also AGL works towards this. Now, we have more layers than just OE core, right? So we have more to do. So since Kirkstone, Yocto Project 4.0 Kirkstone, the reproducible builds are part of Open Embedded Core. So we can make use of it. We have it on, it is actually on by default. We do just two settings on top to make also our images reproducible. We set these two, one affects the sources. We set all sources to this timestamp, and we set the root FS to this timestamp. Now, having full reproducible builds has important effects. It means that you can rebuild binary identical images in the end at any time. It also means that your binary cache, right? Remember, BitBake as the engine has a binary cache, the S-state cache. It also means we can reuse the binary cache way more efficiently. And fully reproducible builds also support you when you do offline builds. Let's take a quick look at BitBake and how it does the build. In principle, we use a limited set of host tools. In the recipes, we define the sources, we define the options, and then we can create hashes over the sources. We know we use a tarball. We can use a hash from the tarball to identify that. The recipe metadata and this hash, we can create a new hash over here. And for the next recipe, or for a recipe that depends on the first one, yeah, we can do the same. So we actually have a full tree of hashes throughout the build process. So what happens now if one source changes? Well, this hash changes, right? So that is the first piece that changes. And we know that essentially that hash is part of the recipe. So this changes, we need to rebuild this. This hash changes, we need to rebuild this. This hash changes, and so on and so on. So we know exactly the chain of events that is supposed to happen once we have, for example, a source change over here, because all the subsequent hashes will change. Okay, now, quick recap. To speed up your builds, OpenEmbedded and Yocto do provide a couple of variables that you can set and use. So there is the LDR, and the LDR does here act on the fetching of the sources. So instead of going out to the internets, we will look at this directory first. We have the state_dir. The state_dir is the binary cache, and that will act on a number of places because we have at different in different sections of the build process, we have binary outcome, essentially. So this has multiple binary artifacts. It can be reused, and it is basically speeding up the builds quite a lot. You can also set bbgenerate mirror tarballs, and you can also set premirror. Premirror is the location where if we have to go out to the network, we check there first. So a premirror would be a mirror that can be on-premise, yeah, local to your workgroup, company, your home. So that can be used to cache sources more closely to your machine. And that's the chain of events. First we check premirrors, then we check the source URI, so the actual URL provided in the recipe, and then there's a backup, and the Yocto project hosts a set of mirrors. So in case sources vanish from the internet because, let's say, a project cleaned up their download server, right? Happens all the time. An artifact is no longer available. So the Yocto project has this mirror available. And AGL, on our download server, we also do provide a mirror for certain packages. Not all of them, but most. To help you, there is, beside generate mirror tarballs, there is also the archiver class that you can use, and you can configure the archiver in this way, and the outcome of this will be something you can put on a web server and point your build process towards as a premirror and be done. So this is the way how you would fill a premirror essentially. And essentially, once you have a local premirror, you could set bbno network and tell bitbake to only fetch from the premirror. What's the outcome of this? Essentially, this is a full offline build then, right? We do not go out to the internet, and it means you have the complete set of sources relevant to your build local. Also, we can do the same for the binary cache. You can put your state dir on a web server and point state mirrors to that. So that allows you to speed up the build because we can query the step after building, and that will speed up the whole process. Good. Now, reproducible builds exactly help here because we can then go to our either state directory or to our state mirror. Now, another aspect of the reproducible build is that if we have a reproducible build and there is a change happening, let's say package X gets a change, let's say we need to fix a typo in the documentation, right? So this does not affect source code at all, right? It affects the documentation. And then we still need to change the recipe, right? Because it's a different tarball or Git revision that we use. That will trigger a rebuild. But the binary that, well, is supposed to be installed on the target system did not change. It's the documentation that changed, but not the binary at all. So usually this change over here would trigger a rebuild of everything that's below here. There is a new hashserve component that you can use with bitbake builds, and that will basically detect this and say, okay, we have a change, but it did not affect the outcome here, so we do not need to do the full rebuild. Yeah? So this can A, speed up your builds locally, and B, it can speed up the builds because if we detect that, we can query the state mirror, for example, or your state directory. And so this greatly speeds up the build process. There is a talk about OE self-test, and there is an OE self-test for reproducible builds. So I recommend that talk. It's after lunch, and there I have time to talk about a few aspects, how you can test your images for reproducibility. So let's continue that discussion then. Okay, so to summarize, reproducible builds help you on multiple aspects. Maintainability, of course. Build performance-wise, if your builds are reproducible, you can make use of the caches way more efficiently. And it goes very well together with the bit-bake, either local or network caches, right? So you benefit in multiple areas here. Let me talk about software bill of materials. So yesterday there was a good talk from Ito-san, in short, reproducible builds are there because we need to understand how our, well, house of cards is constructed and how our software stacks are built. Yeah? So that applies to Log4j, that applies to, well, databases, libraries, just pick. Outcome for us, TLDR, SBOMs are or will become mandatory for us. What is an SBOM? An SBOM is in principle an inventory of the different well, components that make a piece of software. Where did it come from? What version is it? In principle, it is the evolution of the software licensing efforts that were happening, and we are adding more data here. Of course, we track the licenses as well, so we can answer then for an image if and what licenses we use, and then we can answer the questions if we are complying with the software licenses. We can also say, let's say from the version or from the patch state, from the hashes, we can say if let's say an image would be vulnerable, right? Because we have each software component listed. We have the version of each software component listed. Well, there are the well-known databases, CVE, for example, and then we can say, okay, we are using version X. Version X is now known to be vulnerable. So from an image, from an SBOM, we can actually say those CVEs do apply to this image, without looking at the content of the image, just from the metadata. So it's basically a set of metadata, and we can act on the metadata that we have there. In principle, we are adding an SBOM through metadata to an image. We then essentially need to track back to the code, right? So the SBOM is attached to an image, to the binary, and we need to trace back, right? To some extent, we can do that because we can then use the hashes that are embedded in the SBOM and say, wait a minute, this binary on the target has not the same hash, right? So we could even say, there has been something tampered with. So SPDX kind of looks like this. It's not really human readable and likely not supposed to. But you see, we track hashes, we track different things, files, package information, and so on and so on. So for IGL, Yocto and BitBake make it easy. We enable create SPDX BB class, and for AGL it is easy to do because we have a flag you can just set. Okay, so Yocto and BitBake allow us to just turn this on. The output will be next to your image. It's a tarball, and it contains an index file with references to the individual SBOMs. Note that not all tools or in the SPDX universe do yet like the references in that index file, right? So there is a gap in the tooling, and the files in here are perfectly fine with the spec. It's the tooling that needs to catch up yet. Why does it jump? Anyway. Okay, so here you just turn on AGL create SPDX, and you get this tarball, which is 11 megabyte. Uncompressed is 175 megabyte. Right? So it's all text. Yeah? So this is a lot of metadata. Okay, let's jump a little back. Remember, we had hashes in here, yeah, for every step essentially, right? Let's keep that in mind. We have the SBOM information from the target image, and essentially that kind of records this as well. So in principle, we can track back through the metadata, right? We have all the pieces, so we can essentially, from the SBOM, we can track back up to the original sources, for example. So we have all the pieces, actually, because each step does produce SPDX metadata, and we basically can follow that chain back up. That tooling does not exist yet, but it's being worked on. Also, SPDX is being further developed. So the new SPDX version will have additional, I think it's called profiles, kind of, or different types of SPDX. And so BitBake and Yocto are well suited to write out that SPDX metadata and record it. Yeah, so there are relationships. So I recommend that, this presentation from Joshua Watt. It's in the references in my talk. I really recommend that. It's way more detailed than we can cover over here. So why does it go so well together? Again, let's put those pieces together. Reproducible builds mean we have a deterministic path from source to binary, right? The SBOMs basically record metadata to the binary and to the image in the end. And we can use this to track, for example, CVEs at a later stage without looking at without finding, oh, this image was built with this tree and that and this and that. So we record, essentially once a build is done, right, we lose a lot of information, remember? At the end we have an image that we put on an SD card, but we lose all of this information, how it was created. And the SBOM essentially tracks that information. Essentially, there could be a way to track back from binary to source. There are already tools out there, for example, Gripe. Gripe takes an SBOM. You can feed an SBOM into Gripe, and it fetches the NVE database, the CVE database, and tells you, that's the open issues right now. Yeah? So there is interesting stuff that you can do then in the end with an SBOM, but there is still a tooling gap. The tools need to evolve. The ecosystem around SPDX is evolving rapidly. There are online tools, online checkers. There are tools that now evaluate SBOMs and give you additional information. So there is more to come and more that we can look forward to. Okay, any questions? Yes, please.
You also you talked about that these activities done in Yaokt project, and do any other similar activities in other area of Linux Foundation? Not only on the
the Linux Foundation has the SPDX, hosts the SPDX work group, right? And the Yocto project is working within the SPDX work group on defining the next version of SPDX. So people from the Yocto project are at the forefront here. And essentially, we will record more information during the build process, right? So there will be multiple types of SBOMs, basically SBOMs generated during the build, SBOMs generated through scanning, SBOMs generated at whatever other point. So there are multiple new versions of the SBOMs coming.
Thank you very much. Yeah, it's Koji Miyake from Synopsys. Thank you very much.
I think one more question. Yeah.
Oh, okay, thank you. So how can we assure the correctness of the 175 megabyte SPDX data?
How can we ensure the correctness?
Correctness. So yeah, on the format, it is easy to check the format by using a tool, but contents of the SPDX it is difficult to find that SPDX contents is correct or not by tools, because some tools fail to detect the license information. So how can we assure the correctness of the contents of the SPDX?
For what aspect? Licensing?
Licensing, or that not depends on the licensing, but also in vulnerability information. So some tool.
SPDX has different So one of the let's see, contains, it's not in here. So SPDX has one field that tracks if this data was automatically generated or if it happened through a review process. So the way how the SBOM was obtained is also being tracked. If this was kind of a manual inspection process or if it was generated by a tool, this is being tracked in the SBOM information.
Okay,
so you can, I mean, you can track if it has been kind of manually verified or if this has been auto-generated. Yeah.
Okay, okay, thank you. So current SBOM format has a flag that is generated by tool or reviewed data. Or so, I don't know how we do it, but some manual review can cover the tool's faults.
There are review tool chains available and possible, and there are kind of commercial tools that will scan your source code. There are open source tools that will scan your source code. So basically, we are not there yet to make use of every piece of the puzzle, agreed, but you could combine kind of a scan of the source with the tooling here to further enhance the quality.
Okay.
Yeah?
Okay,
It's
thank
one,
you.
we are step by step.
Yeah.
Yeah.
Thank you.
Okay. All right, thank you.